So like today we'll basically go through some inequalities in geometry. And the first part is like Ptolemy inequality and its applications. Oops. Oh, I shouldn't. And like the first problem is like the Lamke inequality, and like it states that the three edges of the triangle are denoted as ABC, and you have the midlines, and you need to prove that the inequality holds. Like the neatest solution only needs a geometric figure, and like um like maybe you can think about this like for some time, but like the construction is actually pretty really neat. And yeah, I guess I will just review this one. Like I suppose you actually draw a random triangle and we name it as like ABC. Oops, suck. And like you may wonder, how could we actually have like maybe 4MB and 4MC? And like you may think of like we need a parallelogram so that we can actually have like twice the length of the midlines. So like it's natural for us to construct like maybe something related with parallelograms. And this way, and after you construct this way, you may actually realize that like DE equals to twice the length of BC, aka D equals to like 2A, and BD is twice the length of the midline, like of the edge AC, because we know it's a parallelogram. So BD, oops, so BD just equals to 2MB. And like similarly, we know C equals to 2MC. And like, I suppose you know the Ptolemy inequality. And like, if we use the inequality in the like quadrilateral BCDE, you could actually like write this up like BC times DE plus B times CD is bigger or equal to BD times EC. And you just need to like substitute like the values of each edges we have written above and the inequality. Like you just prove it. Like this is the most elegant way to prove it. And I think the key is to just like you need to think of constructing parallelograms, because like you see some conditions like maybe twice the midlines. And yeah, this is just maybe some warm up. Like, and the second problem is also related with midlines. Like it states that in a triangle ABC, and we have the three midlines, and we need to prove like this very goofy inequality. Like why is it like bigger or equal to 0? Like I don't think it's evident. Like you may want to think about it for some while, how you can like actually connect the product of different edges to the square of the other edge. And the hint is that we need to find like a specific quadrilateral in which we can use the Ptolemy inequality. But like it is some general saying, and actually if you have no idea, we can just like draw the graph. We draw maybe a random triangle ABC. And we know G is the centroid because like we have 3 midlines, and now we wonder which quadrilateral we should use, the Ptolemy inequality. And you will realize that there aren't actually many quadrilaterals existing in this shape. So like we only have maybe BDGF, CGD, and AGF, which are obvious. Like you may think of using the inequality in BDGF because it is related with midlines, and you know BD and BF are some like non-edges because you know AB and BC. So we can just use the Ptolemy inequality in the quadrilateral BDGF, and this way we know that BG times DF is smaller than GF times BD, and plus DG times BF. And we know BG is like 2/3 of the MB because G is the centroid, and DG is like 1/3 of MA, and GF is 1/3 of MC. DF equals to, oh yeah, we also need to connect DF, and DF equals to half of AC, which is half of B. So like we can rewrite this equation into 2B times MB is smaller than AMC plus CMA. And like right now, you can observe what we want to prove, and you can think of like maybe we should time something like on the both sides of the inequality. And since we need square, we just like time B, and it will just becomes to B squared MB be smaller than ABMC and CBMA. And similarly, if you use like the Ptolemy inequality in the quadrilateral CGD or the quadrilateral AGF, you could get something very similar like to this inequality, and you know, like finally just sum them up, and the problem is proved. So I guess like the key to this problem is just like you need to know, like I think maybe the first thing is to think of like using Ptolemy inequality, but like it is not that hard because like you know you need to use the conditions of midlines and like the centroid. So like just think of using Ptolemy inequality, and it's not hard to find quadrilaterals because there aren't any like initially. So yeah. And the third problem is a bit like complicated and strange because like it seems to mix with some trigonometry. Yeah, I think you can just first like maybe read this problem because it's like a bit strange, and because like on the left hand side we have the sum of some edges, and on the right hand side we also have like the sum of edges, and but we need to maybe time an angle, and I think it is very hard to start with, so maybe start with something small is a good idea, and that's why I say we should focus on tiny part like in this problem. um Well, I think you can think of it for some time, because like it's not evident. Like you will notice that you cannot tackle this problem as a whole, because like you don't even know like what n is. You may think of induction, and you can try that as well. But like I think we should just focus on like some tiny part. And so for example, like I will just draw some random point. We name it as I minus 1, and this is AI. And maybe this is I plus 1. And you can like connect them. Oops. And since like mi is the middle point, so does mi minus 1. So mi lies here, and mi minus 1 lies here. And we know P is just some random point. So I'll just put P here. And we connect Pm minus 1, Pmi. And we better connect this two as well, because like they have some relations. And now we need to use the Ptolemy inequality, like in the quadrilateral Pm minus 1, AI and IMI. But like you may ask, like, how can we think of it? In cases like you don't have a lot of quadrilaterals from the beginning, and you need to prove such a goofy inequality, so it is something related with like geometry inequalities, and you need to tackle this problem from like small part. So like if you use Ptolemy inequality in this quadrilateral, you could actually get AI mi minus 1 times Pmi plus Pm. Oh, I can't write. Pm minus 1 times AI mi be bigger than PAI times mi minus 1 mi. And this is obvious because we know the conclusions. And like in this way, we can tidy up the inequality with their like mathematical relations. They possess themselves. And it is a small jump here, but like I think it's easy to understand that after tidy up, you will get Pmi plus Pmi minus 1 be bigger than 2 cosine pi over n and times PAI. And like since you need the sum, you just need to sum up the equation we get, and that is the solution we want. So I think the key to this problem is to think of like you need to use inequality in quadrilaterals, and like you need to like actually break this problem into some small parts so that you can tackle them instead of thinking it as a whole. Because like if you think it as a whole, you may not even know where to start, and this is not good. So it is just something related with Ptolemy inequality, and like I put some problems related with it in the problem set, and yeah, I think they're interesting, maybe to some extent. And the second part is just like linear geometry.
How does this 2 cos pi by n come?
What? Wait, actually, who is speaking? I'm sorry, I cannot understand.
Oh
Like,
yeah, so like how does this 2 cos pi by n come?
can you type in chat? I
Yeah,
really.
yeah, sure. Oh, is it not fine? You're on mute, by the way, if you're saying something.
I think it's like you need to like look at it separately, because like um
Yeah, so what I was trying to do is like AI M I minus 1 is like twice of, oh no, it's like AI minus 1 half, and then AI Mi is like AI plus 1 by 2, and similarly Mi minus 1 into Mi can be written as AI minus 1 AI plus 1 by 2, and then you can try using cosine rule, but that gives something else, no?
I think it's like it is a regular n-gon, and the cosine pi, like pi over n, is the like the angle. How to describe it? Like pi over n is the angle here. Oh, shoot.
You can do control.
Yeah, it on pi over n is the angle here. So like if you think of like cosine pi over n times PAI,
Shouldn't pi by n be the like exterior angle?
cosine pi over n is like half of the angle, like angle formed between AI minus 1, AI plus 1. So like
That angle is n minus 2 into pi by n, no? Not pi by n.
Yeah, that should be the exterior angle.
So we have to find mi minus 1 mi by ai mi minus 1. We can calculate the angle ai mi minus 1 and mi. That is just 180 minus n minus 2 by n into 180, which is 360 by 2. 360 by n by 2. That becomes pi by n. And then you take the cos of that. So you
Oh,
get
right.
that.
Okay. Yeah, fine.
So is this solved? I really like don't get you, because yeah.
Yeah, I guess so.
So the linear part, like the first one is like a very famous inequality, and there are like a lot of ways to prove it. And like the earliest proof is very bashing, and like I hope we could prove it in a like neater way related with area. So I will just draw the graph first. Like the earliest proof is related with like trigonometric bash, like something related with cosine, and yeah. But like today we'll just go through a better proof. I mean, in my sense, like you have P here.
Maybe
Yeah.
maybe you can reflect P around the sides and you'll get a hexagon.
Like he said that we can reflect P over the sides A, B, B, C, and C, A, and then form an hexagon.
Well, actually, I think that sounds cool, but I'm not sure if it works. But like the one related with ratio is just you have P here, and you kind of form a similar triangle with ABC. Like you have a line, call it MN, and like you enable the angle AMN equals to ACB, and you have a similar triangle. So that we know AN over MN equals to C over A, and AM over MN equals to B over A, because like it's kind of the same with the like bigger triangle. And since we know AMN is the sum of AMP minus AMP, we know AP times MN is bigger than Q times AN and R times AM. I think I will write this down. Like left hand side is bigger than or equal to, because like we don't know if AP is the length of the triangle AMN. So it is bigger than Q times AN plus R times AM. And Q is the length from P to AC, R is the length from P to AB. So the inequality holds because of the relationship area. And like we just get rid of MN from both sides, and we have AP is bigger than or equal to Q times AN over MN plus R times AM over MN. And which is X, which is AP, is bigger than or equal to C times A. C over A times Q plus B over A times R, which is what we get like above the ratio of AN over MN and AM over MN. So, oops. I will clear this. And so what we get is that AP, oh, shoot. AP is bigger than Q times AN over MN, and we know AN over MN is C over A, because like the similar triangle we construct, and AM over MN is B over A, so it's plus R over R times B over A. And like similarly, you do this to Y, like which is PB into Z, which is PC, and you could get like 3 very similar inequalities as this one, and you just sum them up, and you'll get X plus Y plus D is bigger than or equal to P plus C over B plus B over C plus Q times C over A plus A over C, and R times B over A plus A over B, and which is twice P plus Q plus R. Then I mean it is bigger than or equal to 2 times P plus Q plus R, because we know like C over B plus B over C is like bigger than 2, right? So like it's done because you construct a similar triangle and you get the ratios of different edges, and you use like the relations between different areas, and you finally sum them up and use the basic inequality at the last step. And I think it's very elegant proof. I think if we have more time, we will go through like some other proofs. Yeah, like some of them like let us prove a stronger inequality. Yeah. Anyway, and like the second problem is like a good example of showing us like we can prove an equality by proving its stronger version. And I think my description may be a little confusing, but like HA is the altitude of the edge BC, MB is the middle line of AC, and TC is the like the angle bisector of an angle whose opposite edge is AB. So like it should look this way. Oh gosh. And this is HA, and like this is MB, and TC is just the bisector here. And the key to this problem is that we want to prove a stronger version of it. Like, maybe you have no idea why this inequality is true. And like, how can we actually prove a stronger version? You may think of change one of HA and IMOTC. And like, it's natural to think of changing HA because we know like the altitude is the shortest edge from one vertex to the other, like the other land edge. So like, it's natural to think of changing HA to something else. But like, what should we actually like exactly change it into? You have two choices, like maybe change it to MA or TA. And I think you may want to change it to TA because like the angle bisectors have better properties, like their middle lines, because it have angles. So like if you change HA to TA, we want to prove the stronger version, which is TA plus MB plus TC. It's smaller than skirt 3/2, like A plus B plus C. And this is the stronger version. And but like, how can we actually prove it? I think, wait, let me see the chat. Oh, and yeah, like we know sometimes we cannot tackle the problem as a whole, but like we know there is some magic happening if we actually maybe sometimes sum up some inequalities. So like we can just prove something maybe partial, and like we could think of proof that MB plus 2TA is smaller than skirt 3/2 B plus 2C. Like, you may wonder, why is it true? I mean, like, you will notice that if it is true, then we also have MB plus 2TC is smaller than skirt 3/2 B plus 2A. And if you sum this up, we could get this one. So like, we just need to prove one of them and the rest are all set. So, well,
Okay, how did you get this MB plus 2T thing?
She hasn't yet. She told that she will do it right now.
Oh, okay.
yeah, like we haven't proved it, but like we want to prove it because like if the above is true, then similarly the below one is also true, and we can get the stronger version. So like,
Yeah, okay.
let's prove this one, I guess. Yeah, I need to clear the drawings. And well, like next we need to use some formula related with like the bisectors. And well, maybe I should still draw the graph here. This is the altitude HA, and this is the bisector TA. And by the formula of the angle bisector, we know that TA square like equals to, well, I assume you know that, but like I'm actually not sure for over B plus C square and times BCP P minus A. Like this is just some formula. And I think, well, maybe it is bad. And like we know for BC over B plus C square is smaller than 1. So the equation can just be write as the square of TA is smaller than P times P minus A.
Oh, what is P?
P, I think P is the like half of the circumference of the triangle ABC.
Oh, okay.
And like you get this one, which is smaller than or equal to P times P minus A. And well, and like you can just like substitute P in, which is half of the circumference, and you clear it up, you can get like a quarter of the P plus C square minus A square. Like, yeah. And like there is some other formula related with middle line, which is like a bit more famous. Like we know the square of MB equals to quarter of 2A square plus 2C square minus B square. And then we need to use Cauchy to relate this two. And well, we need to use Cauchy with MB and TA because like if you add them up, you could actually get B plus 2C, which is what we want to prove. And yeah, I need to clear this up. Like maybe I should write smaller. And if you use Cauchy with MB and TA, you could actually get that MB plus 2TA is smaller than or equal to skirt 3 plus MB square minus 2TA square. I will just write this down quickly. And this is smaller than or equal to 3 MB square plus 2TA square. Because of Cauchy, and you just substitute what we have got like above, and this can be written as smaller than or equal to 3 over 4 times 2A square plus 2C square minus B square plus 2B plus C square minus 2A square, in which is skirt 3 over 2B plus 2C. And thus we're done. Like, I mean, we're done with the partial inequality, but like based on what we've introduced above, the problem is also done. So I think the key to this problem is, well, like you need to realize you need a stronger version of the inequality we want to prove, and you can transform the altitude HA into like the bisector TA, like instead of transforming it into middle line. I don't know if middle line could work because I haven't tried. Maybe I will try it like later. And well, and the next problem is interesting. I mean, by interesting, I mean like it will need some trigonometric bash at last. So it is not good. But like I think the conclusion is famous. I'm not sure. So if you have a triangle ABC and you just, oops. And here is I, which is the incenter. And we also have G, which is the centroid. Oh. And we want to prove that AI plus BI plus CI is smaller than AG plus PG plus CG. I mean, without laws of generality, we can just assume that BC is bigger than AC than AB because whatever is all the same. And the key to this problem is to think of like where G can be, like where the centroid of a triangle can be. Like the centroid in our common sense can only lie inside the triangle or on the edges of the triangle. So, but like where does the point lie actually? Like besides what we know obviously, like its relationship with triangle ABC. Yeah, it is actually tricky here because we want to prove that G must lie inside or on the edge of triangle BIC. So we first need to prove that it doesn't lie in the triangle AIB. But like you may wonder, like, why not? So it is what we need to prove. So like, suppose G actually lies in the triangle ABI, then we know the area of triangle ABG is smaller than ABI. But since ABG is like 1/3 of the whole triangle ABC, we know that we need the area ratio here. The area of triangle AIB over the area of the triangle ABC is C over A plus B plus C, which is smaller than 1/3 because we've assumed that A is bigger than B than C. So we know like the area of the triangle AIB is smaller than 1/3 of the triangle ABC, but like 1/3 of the area of the triangle ABC actually equals to ABG. So we know the area of AIB is smaller than ABG, which contradicts our assumption because we've assumed that the triangle ABG is smaller than AIB if G actually lies in the inside of the triangle ABI. So we know like G doesn't lie inside of the triangle ABI because of the area ratio and the contradiction. And on the other hand, we need to prove G doesn't lie in AIC as well. Like we assume G actually lies in AIC, then we can assume that CI and AB, like they intersect at T. I will draw it. CI and AB intersect at T, and CG. Oh, I will just draw a random point here. In CG and AB intersect at L. Then we know that AT is bigger than AL, right? So, and we also know AL equals to BL because G is the centroid. So AT over BT just equals to B over A, AT over BT just equals to B over A. And which is like smaller than or equal to 1. So AT is smaller than 1/2 of the AB, which is equal to AL. And that's a contradiction. So G doesn't lie in the triangle AIC as well. Thus we finish our first part of proof that we know G lies either inside of the BIC or like on the boundary of it. And there is something like more specific. We can also prove that G actually lies on the right side of AI. And because like we can assume the, how to say that? We can assume this angle as theta, and AIG is obviously pi minus theta. So theta is bigger or equal to 0, but smaller or equal to half of the angle A plus C. So we know AG is bigger than or equal to AI plus GI cosine theta. we know AG is bigger than or equal to AI plus GI cosine theta. And like similarly, you can get to inequalities related with BG and CG. Like BG is bigger than or equal to BI minus GI times cosine. Like 90 degrees minus C over 2. Oh, oops, plus C over 2 minus theta, and CG is bigger than or equal to CI minus GI cosine A plus C over 2 minus theta. Well, yeah, I think I need to write this down. Like, it's just something like you can notice in the graphs we've drawn in and thus, you know, like AG plus BG plus CG minus AI minus BI minus CI is like oh, you mean the most basic one? It's like AG is like bigger or equal to AI plus GI cosine theta, because like you don't know if like if you actually draw a perpendicular line from G to the to the line AI, then like AG is bigger than the it's bigger than oh gosh, I can't English. So here is G, and here is A, here is I, and here is theta, and you draw a line here. So AI plus AG cosine theta equals to this one, but like AG is bigger than or equal to because like it is it has a 90 degree, so AG is obviously like bigger than or equal to like the length on the left because like yeah, oh gosh, I really can't English. So like we know AG plus VG plus CG minus AI minus BI minus CI. I'll keep writing this. Like this one is bigger than GI cosine theta minus plus this one. I'm too lazy to write, and minus this one. So like next step is just some trigonometric bash, and I'm actually lazy to write them. So maybe you could think of it like how you could bash it, like the relationship between different angles and cosine. Like you need to cosine theta plus cosine 90 degrees plus C over 2 minus theta, and like the other cosine formula, like how can you relate them? Yeah, it's just some heavy trigonometry bash, because and the essence here is just you know you can write cosine 90 degrees plus half of C minus theta, and here is cosine A plus C over 2 minus theta. Like you need to transform this one, and this one is like you may think of like you can write 90 degrees into A plus B plus C over 2. Or you can actually just expand it, and finally you will get some result. I will I will not calculate because it's too heavy bash. Well, yeah, I guess I will just be lazy and leave this to you. Anyway, finally you could get something like out of this, and you will use something related with what we know of the like the sum of the degree of a triangle, and finally you could literally prove it. But I'm lazy and I will skip it. Yeah, but let's just pretend nothing happens. Well, in the rasters, there's something like circumference related, like the first theorem are obvious. And I think we'll just skip the note for now, because like you may actually recall something like we've proved of the cosine one, but like we won't prove it for now. Like we could, because like the first note is obvious following from theorem 3.2. So yeah, but like we won't take time to prove them, because like the rest of the problems are much more interesting. And well, the example, like the first example 3.5 is very classical. So it says that if the curve L divides the equilateral triangle ABC into two parts with equal area, then we prove that L is bigger than blah blah blah, among which L is the length of the bigger L and A is the length of AB. So basically, like we draw a triangle ABC, and we have a curve L, and we know like L divides the area of the triangle ABC, and we want to prove it. But like, how can we prove it? Like you have squared pi, and you have like something even more strange. Like this problem is so classical, and I wonder if anybody has ideas, like how can we prove it?
Or we can like maybe join the endpoints. And then those endpoints will approximately divide it in equal area. And the length of this curve is greater than that straight line for obvious reasons. And we can try to bound that straight line rather.
Yeah, I think drawing the endpoints is the exactly right idea. Like if you rotate ABC 6 times, you could actually get something like very beautiful. Like if you reflect it 6 times, you will get something like looks like this, and it will just be oops, like the curve will just form something random, or not random, like it will form something looks like this, and we know like this equals to 3 times the area of triangle ABC, because the half, like the whole, is 6 times the area of triangle ABC, so half is 3. And like from theorem 3.1, we know like when the curve forms a circle, the circumference is the smallest. So we want this random thing to actually be a circle so that the circumference can be smallest, which means 6L is bigger than or equal to 2 pi. And this is just square root 3 times ABC over pi, because like this is the radius we could get. Like we calculate this to get the radius of the circle, and you just need to like to write the area of the triangle ABC in math formula, and like which is not hard because you know, and like in this case L is an arc, and this is L, this is 60 degrees, so you can use L to present like the area of the triangle. Oh wait, whoops, we also know A, so this is not hard. We know like the area of triangle ABC is just like, well, square 3 over 4 A square. So substituting, and you could get it. So like the idea is that you need to connect the endpoints and you rotate them. And you also need to use the theorem 3.1 because like we know over all the like geometric figures which have the same area. Oh yeah, it was indeed slick. Like you rotate them and you're done. So this is just something to entertain. And well, the next one is actually also very slick, like this kind of question. So we'll just maybe just draw a quadrilateral, like, well. So here is A, here's B, here's C, here's D. And we know A, oh, this doesn't hold true in the graph or whatever. And we need to prove that the area of this quadrilateral is smaller than or equal to 3 square 3 over 4c squared. Like it kind of has the same idea with like joining endpoints, but not exactly. Well, I will just do it because it's also fast. So like we can take the edge with the biggest length, which is D in this case, as the axis, and we just like flip it, and now you can get something like here is A, here's B, here is C, and we know like the circumference of this sexagon is like twice A plus B plus C, which is a fixed value. And like based on the theorem we've introduced above, I mean, we didn't really introduce it, but like it is on a handout, and we know like since the circumference is fixed over all the n-gons, the regular n-gons have the biggest area. So like we know the area 2F is just smaller than or equal to 3 square 3 over 2. And A plus B plus C over 3 squared. And since A, B is smaller than C, we can know that F is smaller than or equal to 3 square 3 over 4 C squared. And
How do we know that area is largest when it's regular?
Oh, I think because like over all the geometric figures which have the fixed circumferences, the circle has the biggest area, and over all the n-gons which has the same circumference, like the regular n-gons have the area. Like,
Oh, right. Okay. Yeah. Right.
yeah. Well, I didn't really prepare the proof. Well, maybe I should think of it. I don't know it. But like I think, well,
Yeah, it's fine. I got it.
yeah. And like this one is just the same as last one. You may think of like just connecting endpoints. And yeah, one of the problem set is like we generalize the Popa inequality to n-gon, and it's in the problem set. I think that's really interesting because like we're not considering quadrilateral anymore. We're having more edges. And yeah, in the next problem, and you can see that it has something, the form is really unfriendly, and it is like it looks like some random inequality popping up from nowhere, because it says that like the sum of phi1 to phi-n equals to pi, and phi1 is bigger than 0, smaller than pi. And then we prove that for any non-active real values x1 to xn, we have the sum of xi squared is bigger than or equal to sec pi over n, and the sum from 1 to n xi minus 1 cosine phi I, and x n minus 1 equals to x1. It is like totally random. And yeah, I think the key to this problem is that you need to think of it like from some small parts, like not to tackle this problem as a whole. And one more note is that the inequality can actually be generalized to straight version or like higher version, higher division. Yeah, but like I think we'll just go through it maybe fast, because this is hard. So like you need to think of it like geometrically. And so suppose we have a point and it is named as O, and you have like a lot of lines here. I will just draw someone, and like we let the angle AIO AI minus 1 equal to phi I plus pi over n. And like in this line, we will maybe get some edges OAI to let them equal to xi. So while here is A1, oh, oops, and here's A2, here's A3, here's A4 and a log, and here's AN. So we actually have an n-gon, A1, A2, to AN. And like right now we will assume AI minus 1, oh, oops, AI plus 1 equals to AI, and we denote the area of this gon as F. And so maybe let's just focus on the triangle OAI, AI minus 1. And we use something related with cosine. We know that AI squared equals to xi squared plus xi plus 1 squared minus 2. xi minus, xi plus 1, and cosine the angle AI OAI plus 1. And this is obvious because we have the formula. So you can sum the left-hand side, you will get the sum of AI squared from 1 to n, and you sum the right-hand side, you will get like twice of the xi squared from 1 to n, and you need to minus something. You need to minus 2, and the sum from 1 to n xi plus 1, and cosine phi I plus pi over n. Like you just need to sum them up, and it like it's long, but it's not hard. So here you write it as here is xi squared n plus 2 xi plus 1 and cosine phi I plus pi over n. Like after summing up the equation from 1 to n, and like in the next step, you need to use Cauchy and the theorems we've like listed, and you could get that. Well, I'm not sure if I should write that. I think it might be better like if you think of it through, but like finally we'll get something like this, like the sum of the AI square is bigger than this one because of Cauchy. Wait. And then we will use the theorems we've introduced above, and you can get this is bigger than 2 4f tangent pi over n. And I will not go deeper than this because like the first part you use Cauchy, and the second part you use the theorems above. And well, I guess I will just stop here because like if you like view this to, well, how can I say, like you know the sum of the square, like the AI square from 1 to n, and you also have the like inequality below, you could actually write down the sum of xi squared from 1 to n, which is 2f tangent pi over minus from 1 to n xi I plus 1 cosine phi plus pi over n. But like that is too much. So yeah, I guess I will just stop here so that you could understand like why we could get this so far. And like the later part is just some trigonometric bash and not that important. Yeah, I and like the final part is just something like in three dimension, because I think it is cool like how inequality can actually like work also works in 3-dimension space. And yeah, and the first one is like totally out of nowhere. So I will just draw random stuff. So suppose A is here, and here is B, C, and D. Like I'm not sure if I described D very clearly. It's like, you know, we have the distances between AC and BD, between AB and CD, between BC and AD, and D is the smallest distance of the three, and H is the smallest altitude of ABCD, and we want to prove that 2D is bigger than H. And the key to this problem is that you want to look for, or maybe construct one yourself, like a plane which has a lot of like mass relationships on it. So that you could actually you could transform this 3-dimension problem into 2-dimensional. So, well, so I guess we'll just like maybe draw the altitude first. So here is AH. And here is AH. And we know the distance from between AC to BD is D. And right now we will drop some altitudes, like the altitudes from A to BD. This is F. And from C to BD, this is N. But like, how can you actually like correlate these points or shapes or edges? We know that HF is parallel to CN. So we could maybe form a rectangle FECN in the plane BCD. So I guess we'll need a new point called E. And well, E will just be here. And you connect EA. And since we know AH is the altitude of the triangle AEF, we could think of maybe like drawing the other two altitudes. So you can have EF and EM and FG, and EM is perpendicular to AF. And this one, we call it FG. And like right now, we will consider the triangle AEF, and AH is the altitude of EF. The altitude of AE, which is FG, equals to D, because like D is the distance between AC and BD, which is just FG, and EM is the distance from C to the surface ABD. So we know EM is bigger than or equal to AH. Otherwise, EM will be the smallest like altitude, which is contradiction. So EM will be bigger than or equal to AH. And like so far, we will realize that like all the conditions the problem gives us are collected in the surface AEF. So we just want to prove that in the triangle AEF, AH over FG is smaller than 2. And since we know AH is smaller than or equal to EM, we know AF is smaller than or equal to EF. And we notice that AEH is similar with the triangle FEG. So, and you, so this way you have H over D equals to AH over FG equals to AE over EF. And is smaller than AF plus EF over EF, and which is smaller than or equal to 2. So this problem is that you need to find a surface, like you can put all the conditions the problem gives you to a surface, so that you can transform a 3D problem into a 2D one. Yeah. And actually the example, it is more of a research question than a pure problem, because like, well, how to say, because like it could actually conclude that like of all the of all the stuff with such a shape and they have the same dimensions, you can know that the one with which has the most irregular shape has the biggest width. But like it is hard to explain using such a problem. Well, I think it just conveys that it is more of a research problem than a single Olympics problem. And it is also very neat. But like when I first did it, I couldn't solve it because like I don't know like where I should even start. But like the solution just reminded me of like something, because we need to like put what we know in the triangle AEF, like in a such a surface, we have all the conditions the problem provides us. And the second problem is also from the Soviet Olympics. Well, and in this one we need to use Steiner theorem, and Steiner theorem is like what I've listed in the handout, I guess. So we know like, so we can assume, maybe I will just draw something first. So here we have A, B, C, D, and here is B, here is D, here is A, and here is C. And we will assume the volume of A, B, C, D as V, and what the area of its surface will be as. So, and since like we know R is the radius of the like inscribed sphere, so we know R equals to 3V over S. And since we know Steiner, we could get V equals to 1 over 6 ABD sine theta. And in Steiner, wait, let me see. And D is the distance from between AB and CD, and the theta is the angle formed by AB and CD. It is the Steiner theorem in geometry. Well, I forget to mention it, but anyway, like you from the Steiner theorem you can get it, and like if you conclude like if you put them together, you can get like R is smaller than half of the ABD over S. Because like you are not sure of the sine theta, like you are not sure of the angle, so R is smaller than or equal to half of the ABD over S. And you know, on the other hand, we know like the vertices of the edge AB, like which is either A or B, like the vertices of the edge AB, the distance between the vertices and the CD, like are both bigger than or equal to D, and one of them must be bigger than D, which means the area of triangle ADC plus area of the triangle BDC is bigger than BD. And similarly, we know like the area of the triangle DAB plus the area of the triangle CAB is bigger than or equal. Oh no, it cannot equal. It must be bigger than AD. And if you sum them up, you will know like the surface area of ABCD, which is bigger than AD plus BD. And And then you sum them up, and you will get as is bigger than a plus b times d. And since we know that r is smaller than or equal to 1/2 of the ABD over S, we know r is smaller than ABD over twice a plus b times d, and which is equal to AB to twice a plus b. So this one is just like we all know r equals to 3v over s, and the Steiner theorem tells us the relationship between the volume and its edges and the distance between its opposite edges and the angle they form. Yeah. And like the final problem is very hard. And well, the lemma is actually hard enough. Actually, I think we may just stop here. Like, yeah, well, I'm not too sure. Because like the final problem is literally hard, and the lemma is very confusing. Because like it needs some new definitions in the 3D geometry, like the dihedral angle formed by the surface AI against 2 and the surface AJ against 2, which is confusing description. But like the hint I could give is that you need to prove the lemma first. Like the lemma is not that hard to prove. But like finally, if you wanna prove the whole problem, you need to use something related with Cauchy. And yeah, actually, if you know Polya inequality, you may be like familiar with it, because like the background this inequality was born is related with Polya inequality, which states that S is smaller than or equal to square 3 over 4 ABC square. Then you take third square root. Oh, oops, then take third root. But like this one, I will just skip this one. And the problem set is just like you can see, it is very, very ancient problem set. And I like, since we've introduced 4 sections, I just picked 2 problems from each section. So in total, there are 8 problems. Like I do have answers, but I haven't typed them up. Like, yeah. So does anybody have any questions? I will just skip example 4.3. That's too hard for me to explain. But like you can try to prove the lemma, because the lemma is not that hard to prove. But like the problem itself is just difficult. I mean, if you don't have problems, I think we're done. Yeah.
Yeah, so I guess I'll stop recording in that case.
I think sure.